Tak, lecimy? Okay. Hello everyone and welcome. I'm very glad to see that there are that many persons interested in the exploitation of the slavery work of elemental particles within your machines. My name is Konrad Szałkowski. I'm a Java developer with 15 years of experience. My main areas of everyday work is Java and JVM. I like especially to know what Kitten has inside and how your JVM is running and optimize JVM executions, similar to my previous speaker, Marcin. But when I have some spare time in the evenings, this means the children are asleep, wife is reading a book, I wander into the world of the GPU programming and massive parallel computing available in your machines. You can find me on Twitter, or I should write now X. Yeah, I don't know why X, but okay. And please feel free to use it for the questions afterwards if you have any after my presentation. So, how to make your electrons do more in Java? In short, there are few magic spells known to the code wizards. Here you have some examples. Can anyone tell me what they are? Yeah, those are CPU instructions. Yeah, mnemonics of the CPU instructions. What first three do? Can anyone guess? Yeah, addition, subtraction, multiplication. The fourth one, for me it was the hardest one to guess. Yeah, comparison, good. Comparison. And the fifth one? Yeah, moving memory elements. Those instructions are not just as simple as you say. Those instructions are called SIMD instructions. It means single instruction, multiple data. So one CPU instruction is processing multiple data in completely, truly parallel mode. Within the one so-called cycle of the CPU, you get multiple results while inputting multiple data. Let me give you an example. For example, we have four numbers. Yeah, we want to add them. What would normal Java developer do? Normal Java developer would create an accumulator, go into the for loop, add the first element, add the second element, add the third element, add the fourth element. He or she would do exactly 4 computations. I'm not counting loading the memory, unboxing, boxing, all the stuff that happens in the JVM. Purely 4 arithmetic operations. What would normal code wizard do? Code wizard would put those 4 numbers into sort of a structure and exactly execute one operation and one operation only. V-reduce add. And as a result, he will get the sum of those 4 numbers in one operation. This structure is quite often called vector. And from that reason, SIMD operations are quite often also called vector operations. So where can we find the use of those vector operations? Both integer and floating point ones. So I think first and foremost area of appliance is computer games. Yeah? You must know that this 3D world presented to you in your games is mostly constructed through the algebraic transformations of vectors and matrices. A place where vector operations, from the name also, excel the most. From the games, it's not so far away to simulations. Yeah, so those vector operations are very quite widely used in, for example, computing the airflow around the new car's chassis, or simulation of the flooding of the terrain when someone wants to simulate a disaster and how this disaster should be recovered afterwards. And where else you can find 3 numbers associated together very close, other than in imaging. Your pixels in the screen are often just 4 numbers bound together, and they are therefore very good target and subject of vector operations. Computer vision, computing core range and other stuff like this, it's also widely aided by the SIMD operations. But I would say the most interesting part is the two last appliances, data science. Yeah, in Java and on JVM in general, we have quite a big bunch of tools which are tools for the data science operators. And the most famous buzzword of the last year, artificial intelligence. Because neural networks, which are the salt of the artificial intelligence, are not nothing else than sets of the floating points, floating point numbers. But if such, why these vector operations, if they are so great, why they did not have found an appliance in JVM already? Let me give you a quick history lesson. It's 1996. James Gosling and his team is releasing Java.1. So they are releasing Java to be a language to write software on the Blu-ray discs and Blu-ray disc players. Yeah? Java has one selling point. Write once, run anywhere. In order to cover that, you need to more or less reduce the number of operations you support within your language, and especially within JVM, because you don't want to write that many code to support wide range of operations. Moreover, they were a little bit not pushed to do so because Intel Pentium was at the time dominating the market. Yeah? So what Intel Pentium was? Intel Pentium was a CPU. However great, 30–40% faster than its predecessor, 486. It offered superscalar architecture and a lot of nice things. It even had a, I would say, one of the most famous hardware bugs in it. However, it did not offer one thing. It did not offer SIMD operations in a, I would say, large variety. But then, in the late 1996, there came Pentium MMX. And you must believe me, who owned the MMX at the time was the guy, especially in my neighborhood, because on MMX you could play games, and the games looked much better on MMX than on Pentiums. My cousin had one, and we're going to his home to exactly play some Swift 3D and other games like that. It offered bigger cache, BPU, and it offered MMX, which was the first set of SIMD instructions widely available for people. And the idea kicked in. Yeah? After MMX, there was a response from AMD called 3D Now, and many other instruction sets that followed, and which were implemented on your CPUs in the Intel architecture. Meanwhile, in Java, we had addition, subtraction, multiplication, division, modulo, only on two operands. Nothing has changed throughout these 27 years of Java existence. But I would lie if I would tell that SIMD was ignored completely by the Java. Because I don't know if you know that in your JVMs you have so-called C2 compiler. It's very advanced just-in-time compiler that introduces a lot of optimizations. And one of these optimizations to your code is called superword optimization. And in this superword optimization, what happens? Exactly the code, which is your bytecode, can be replaced by the direct compiled CPU code, which is there in the JVM machine when it detects certain pattern within your code. For example, we have a loop that is iterating over the array of integers, and it's adding them. Yeah, C2 is detecting that, and it takes the pure machine code and replaces the bytecode with the machine code. Yeah, but this happens only for integers. Can anyone tell me why only for integers? Can anyone guess? No, not only integers. It also supports floating points. But the problem is different. Does this equation hold true in the floating point operations? Not always. And as someone will tell, it depends. Yeah? Because the floating point operations in your CPUs are not perfect. They make mistakes because of the representation of the numbers which are there. So this is the reason why C2 compiler do not want to break its contract. The contract says that you cannot differ the optimized code from the sequential one, from the simple one. Moreover, there are JVM intrinsics. Yeah, RI copying, RI filling, comparison of RIs, they are all done within the JVM, and most of the time they are compiled to the SIMD instructions in your machine code. But it was like this till the Java 16. In the Java 16, we got a first preview of the Vector API, which has debuted like a month ago in the Java 21 as an official part of the project Panama, which was released to the public attendance. And the Vector API is an answer to the developer's call, we want SIMD instructions. We want them through the simple and explicit API. And what is most important, we want to know how the JVM will execute our code. So we want a direct compilation to a SIMD code to exactly know which SIMD instruction will be executed by which given construct of the API. And I must say, they delivered. They have achieved it. However, there's a cost. And let me show you this cost quickly by the demo. Okay, let's browse the API first. So, can everyone see? Yeah? Okay. I will scroll up a little bit to even better view. Okay, so where do you start browsing any Java API? In a factory, yeah? So for Vector API, such a factory is called Vector Species. Vector Species is not only a factory of the vectors. Vector Species is an abstraction over the type of the vector. This means the size of the vector in bits and the type of elements which it is holding. Yeah, let's create one. We can create one from the predefined one. In most of the types, and I think right now in the all of them, however, I did not browse the latest release that thoroughly, you have 4 basic ones: species 64, 128, 512, and 256 bits of the vector. You have species max, a predefined constant for a factor, which contract says the biggest supported vector on your machine, comma, period, sorry. While the species preferred says the biggest supported vector, but with the widest variety of the instructions supported. Yeah, so those are very vague, therefore everyone prefers to use the predefined ones because we more or less know where we execute our code. So let's say we use 128 bits. Can someone quickly count how many integers will fit in this vector? Calculators and hands. Okay, 128 bits. By 8 bits in byte, it's 16. 16 by 4 bytes per integer gives you 4 integers in this vector. Yeah? Everything's okay? Now we can start, when we have a factory, we can start to exactly create methods. Species 0. It produces a vector filled with zeros. Species broadcast creates a vector with the predefined value broadcasted through it. Let's use those as an examples afterwards. and use the other one. We can also create a vector from an array. I would say my most obvious constructor for a vector. We give an array to it and the offset of the elements from which it should take. Moreover, we have already in the Java 21 integration with memory API. Who has used memory API? No one yet. However, you can exactly manage memory segments with the memory API and therefore pull exactly these memory segments to your code as a vectors. Okay. What you can do with your vectors? You can, for example, add them one to the other. You can add, what is most important, a result of such operation is another vector, because the vector API is immutable. Vectors within the vector API are immutable. So anytime you perform some operation, you are creating and spawning exactly a new object there. You can, for example, lane-wise execute some operation on this. For example, we can negate all the bits in the vector. We can multiply the whole lane of the vector by 2, for example. You can compare one vector to another. Yeah, it will spawn you a vector mask. You can think of it as a vector of booleans. However, it is not like this. It's a vector holding a result of the comparison operations. Moreover, you can go back from the vector world to scalar world by reducing your vector through some associative operation. For example, add all elements of the vector. And I can show you quickly the library of the operators is very, very big. Those all operations are supported by the vector API. However, their names can be a little bit cryptic, but if you go to the documentation, you can easily read what they do and what exactly will be done on your CPU if you execute such an operation. But okay, a lot of talking, quite nice API. We are playing it around, but let's do something with this API. Okay, let's do our example from the start. Let me scroll for you to see and add some more spaces underneath. Let's add the array of integers. Yeah, we have 123 integers. We want to add them using vector API. And the approach is, I would say, pretty much, sorry, not that vector. Approach is pretty much similar. IntelliJ is against me. We create accumulator. However, the accumulator is a vector filled with zeros at this very moment. Then we are doing a for loop, as you would expect. But we are not jumping one by one. We are jumping by the size of the vector. We can use for that a helper function from our species called length. And using the factory method, which I mentioned already, from array, we create a vector, which we then add to accumulator as one would expect. Yeah. But what may be the problem? We are jumping by fours. Sorry, by 4 integers. Yeah. So we are taking first 4, next 4, so on, so on, so on. What will happen when we reach end of this array? One of the famous exceptions will occur. Array out of bounds exception. In order to prevent that, we need to use a helper function which will bound, as its name says, which will bound the loop iterator to the multiplication of the vector length. Yeah, and therefore it will prevent us from having an exception. We can then reduce the accumulator to a scalar value representing the sum. However, what about these three dangling integers? Sadly, the answer is you need to add them yourself manually. So we create our loop again. We will reuse the I from the previous loop, and we will add the elements as it should be done, one by one, for the remaining three. Let me just escape with the I. Sorry, switching from Mac to Ubuntu. And then we can proudly present our algorithm to the chef, who can pay us for the lines of code. Yeah? You say it's quite a lot of code to write for something that you would normally do with this and get a result. The question is it worth it? And let me show you. I have prepared for you a very simple demo. Yeah, written by complete amateur, it means me. We have three algorithms on the subject here. We have a summing of the 100 million array of elements. We have searching for the max value within the same size of the array. And we have solving quadratic equations. Very naive algorithms, completely simple. And let me show you how the things will look like. Yeah, first is max. First sum. 29 milliseconds versus 21 milliseconds. Then is max. 44 milliseconds versus 22 milliseconds. And then quadratic equations. 300 milliseconds versus 227. Yep. Yeah, you can see that? Okay. You see, the gains are, I would say, substantial. Yeah? For a complete amateur like me who was reading this algorithm by just doing add and multiply and such commands, not diving enough well into the SIMD instructions to pull the whole power of them, I would say the benefits are quite visible. Okay, so cons of the vector API. Lots of code to be written. Yeah, this is a sad downside. Not all of the SIMD instructions, SIMD instructions, are covered. Yeah, there's certain subset only covered, however, quite a significant one in comparison to what we had before. And there's also a downside to the SIMD instructions in themselves. SIMD instructions can also be less accurate when it comes to results. However, there are certain appliances, for example games, when this does not matter that much. Pros? Simple model, I would say. Yeah, API is very simple. You need to know 5 classes most, and you are completely okay to write vector API code. Very explicit usage, so you could say that there's this vector operators library, and I executed clearly SIMD instruction which was underneath. If you dive even from this instruction into the code, into the vector JDK module, which is an addition to Java, you can clearly see the SIMD instructions in the 4 of an array. And there is a significant speed up. Guys from the Apache Lucene, who know what Lucene is? Yeah, quite a few people. So the guys exactly used Vector API in, I think, in the Java 19 edition, I would say. And they boasted about it like 3 months ago. Benjamin Trent, I think, was the one who was presenting. However, they achieved that significant speedups that their QAs and DevOps called them, saying that they must have broken something, because it's not possible that the tests suddenly started to execute that fast. The difference was clearly visible in the graphs. Question is, I always ask myself this question: why now? Yeah, it's 27 years of Java development, and we are getting Vector API at this very moment. I'm not saying that Java was slowly developing, etc., etc., but why suddenly get an interest of this now? I would say that I can only speculate. I do not know the all reasons. However, data science is still growing area. Yeah, lots of code for the data science is written in Java. However, this code is start to be perceived as a slow one. And the scientists, data scientists, are poking into the GPU world where Tesla is the king. Yeah, the NVIDIA GPUs are the king in this world. And the ones sponsoring the Vector API is Intel. You can connect the dots. Well, how is the time? Okay. Question is, sorry, can we squeeze more out of these machines which we have here? What about GPUs, dear Java developers? Yeah, GPU programming in Java? You say, you will answer, okay, nonsense. Like, we should not bother this. Java is not a code for the the GPUs. But we should bother. Yeah? Just because of that fact. Your CPU, yeah? It has 6, 8, 12, 24 computing cores right now. It has a big control unit, big fat control unit, which is able to do a lot of things. DMA transfers, input-output control, a lot of other, lots of stuff. And you have a cache, quite often big one, and you have enormous amounts of RAM. Yeah? While on your GPU, things look pretty much the same. However, you have not 4 or 6 cores. You have thousands of cores. Right now, I think the exact number for the latest 4,000 something NVIDIA is around 3,000 of GPUs cores on the chip. But these cores are purely focused on computing. Therefore, they do not need a big control unit. They have also cache, texture L2 caches, which are very, how to say, sophisticated. Some of them are faster in reads, some of them are faster in writes. So you can pick the cache for your task. And you have also another set of RAM available there, sitting to be used. The problem is not the language. The Java is not the problem. The problem is the different architecture, which forces you, first of all, to have a separate memory management. And we Java developers do not like memory management. Therefore, we have a garbage collector for this. It requires different programming model. Yeah, because of the sheer number of the CPUs or core computing cores, you do not bother with threads. Yeah, imagine managing thousands of threads running in parallel. Quite a tedious task. Therefore, you are having a different approach to this. Just to add a little bit to this point, you are, how to say, You are orientating yourself within the memory, within your task, and you are taking a certain pile of your memory to be computed, and you are only moving around in this memory. It's quite different in order to do not have a problem with memory sharing between the threads. And there are many platforms, yeah? Just to name few, CUDA, OpenCL, OpenACC, and many others are coming. And the problem is handling of those architectures. But there were attempts to integrate those architectures. JCUDA, JOCL. Those libraries are more or less JNI mappings over the normal CUDA libraries which you have available in the NVIDIA SDKs. The problem is that they are JNI mappings, and who has used JNI? I pity you. Sorry, JNI is part of the Java which is not usable. More or less, you are mapping C headers into the Java code with all the problems of the type conversion, handling error situations, and so on and so on. There were two projects kicked in by the Oracle into the OpenJDK project, Project Sumatra and Root Beer. The first one was about bringing the devices through some API to Java. However, but still you needed to have this code compiled in the way that the GPU would understand. So it was only the API to load code to the GPU. And the second one was the Project Root Beer. Root Beer was an attempt to compile via GraalVM, via Graal extensions, a code from Java into the GPU. Both died, sadly. And there are a few other attempts, like JVM on FPGAs. But there's a new boy on the block. New boy on the block is called TornadoVM. It's developed on the University of Manchester, and the guys are doing a proposal how to utilize parallel computing capable devices in Java. And by devices, they do not mean only GPUs. And right now, they do not only mean Java. Right now, they have also bindings for Ruby, Python, and so on. They are using same programming model for SIMD CPUs, for GPUs via CUDA or OpenCL, and for FPGAs. And what you are doing in this TornadoVM, you are parallelizing the closest thing you have in Java to the C code into the actual code which is understandable by the GPUs. So you are compiling static methods. Yeah? You are compiling and adding to them annotations or organizing them into so-called kernels. There are two approaches to how you can run the code on the GPU with Java. And one thing, Tornado is not a holy grail. Tornado does not detect parallelism. It needs your hints to know what can be parallelized. Let me quickly show you the demo of annotation approach, because I think this is the easiest one, especially for the Spring lovers. So, everyone see? We have two methods, two static methods. First one is parallel initialization. We take an array of the floats, we initialize each float with the integer value from the iterator. Yeah? We are adding quite neat annotation at parallel, and this does magic for us. Then we are doing compute square. Yeah? We are taking the array of floats, we are doing a for loop, and this for loop, we are adding annotation at parallel, and we are doing S square over the elements within this for loop. This annotation is this actual hint which you are giving to the TornadoVM to check whether this code can be parallelized on the GPU. So what happens next? You create a task graph. First of all, you create your array, of course, because without the data, they cannot exist. So first, you can create a task graph. Task graph is a plan of your execution. You transfer your data to the device, yeah, to the memory of the device, you create a first task to be executed into the GPU. You create the second task, which is to be executed on the CPU, and you are transferring your results back from the CPU to your own home world of the JVM. Then you are doing some execution plan, blah, 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 and you present the result. And let me quickly show you how you can execute it. You are not executing via this pure Java. You are executing this via instruction called Tornado. Boom, everything was executed on the GPU. What was happening here? First of all, transfer to the device, a workhorse for the memory management. What this method did, it allocated the memory on your GPU RAM, it took your data, it transferred it to the GPU. Then, first task was taken, the Java bytecode of the static method was taken into the Graal compiler. It was compiled to the so-called GPU kernel, and this kernel was loaded into your GPU. The GPU took this kernel, put this code on every CPU it had, and did what is meant in the function. Exactly put a certain number assigned to given function. Then it did the same with this compute square. Yeah, took the static method code, compiled the bytecode to the C code. C code goes to GPU. It is doing the square computation, and afterwards it took your results, transferred back to your array in a safe, managed manner, and given you back the results. Yeah, simple as that. And how are we with the time? Okay, we have 5 more minutes, and let me show you one more thing which I always like to show because it was my study project at the time when I was in the university. We will have problems, but okay. This is ray tracer. Who know what ray tracer is? Oh, quite a few of them. So more or less, in short, it's a simulation of rays going through some 3D scene. Yeah, a rays of light going through the 3D scene. Each pixel is computed separately with the code, and it's going, I would say, like from your eye until it reaches either the background or element of the scene. So we have a light source, 5 balls, and we are pulling on the single core CPU, amazing 2 FPSs. Okay, you say, oh, it's pure Java, by the way. It's pure Java code. We try to make things better. Let's use all the CPUs. Let's use Java parallel streams, fork join pull, and let's put the workload on the whole CPUs. We are pulling amazing 5 FPSs. If I enable the physics, it will look awful, but it works. You can easily see that this is not the effect we would like to have. However, keep finger crossed. We put the same code via OpenCL on the GPU. Okay, I need to restart, sorry. The JavaFX is not working well with memory transfers. Okay, it's back. Let's go straight to the GPU. Yeah, mighty 60 FPS. Yeah, and even if I increase the number of bounces of the ray to the maximum in here, so 6 bounces, it's not even breaking a sweat when it computes the whole scene. Yeah, we can play around with the parameters. You are not able to exactly bring the thing down. Okay, so to quickly sum up, hit benchmark run. So TornadoVM, thanks to the guys from the university, it hides a driver loading the whole hardware stuff for you. It's a, I would say, very big benefit, because when you try to do this in C code, linking libraries, something that we are not used to in Java. It hides memory management. It's not perfect. It's not a garbage collector running there in this memory of the GPU. However, it's already something, and it does not allow you easily to hurt yourself while playing with the memory in the GPU. And it allows you to what we like in Java the most. It allows you on the code to execute within the Java. Moreover, it has so-called dynamic reconfiguration. The Tornado can detect whether the code will run faster on the CPU or in the GPU. Now you say, wait, I just told you that it should run faster on the GPUs. Yes, but there is a certain narrow bottleneck on the way. You need to transfer your data to the GPU via internal buses. And those internal buses is the narrow bottleneck. And this transfer may take time. So Tornado, with its, because it knows the code which it compiles, yeah? It can perform analysis on the code it compiles to C, and therefore to the GPU. It can do heuristics and determine whether your code will run faster on the GPU, or you should better stay at the warm CPU you like. Pros of the Tornado: very simple programming model. Like anyone can learn one annotation. Just one annotation or use a specific kernel API. And we as a Java developers have GPUs at our hand. And the cons are more likely the same, yeah? It's a very simple programming model. It does not allow you to do all the magic it is possible on the GPUs, but it's something. And a lots of boilerplate code again to be written to start a task. Okay, thank you.